Analysis of doubly reinforced beams. We have already learned about singly reinforced beams, where reinforcement was provided on the tension side only. Tension side only. But now it is time to study about doubly reinforced beams. Doubly reinforced beams, where reinforcement has to be provided both tension and compression side. Tension as well as compression side. Why? Why do we provide doubly reinforced beams? Why do we need to provide reinforcements on the tension as well as the compression side? Like this. You see? This is a typical doubly reinforced beam where you have reinforcements on the tension as well as the compression side. Okay, you have reinforcements both on the tension as well as the compression side. Why do we need this? There are 4 reasons why we provide doubly reinforced beams, where depth of the beam is restricted. Depth of beam is restricted. You cannot increase the depth of the beam too much. Due to architectural reasons or any other reasons, you cannot increase the depth of the beam too much. Then you can use doubly reinforced beams. Second, when singly reinforced beam is inadequate, singly reinforced beam is inadequate. Why? We have already learned that the singly reinforced beams are provided where the moment to be resisted mu is less than mu limit. But what happens when mu exceeds mu limit? There we provide doubly reinforced beams. Okay? So in such situations where mu exceeds mu limit, we provide doubly reinforced beams. And what about the next point? Where stress reversals occur. Stress reversal occurs. You can imagine a beam subjected to loads. So let this be a simply supported beam. Subjected to external loads, this beam bends and this experiences a sagging moment. Sagging moment occurs. Sagging moment occurs in this beam. But due to the effect of winds or earthquakes or wind loads or earthquake loads, the direction of load on the beam changes. As a result, what happens? The beam undergoes a change in its stress condition. So here you have compression on the upper side and tension on the lower side. Due to this loading condition, you experience tension on the compression side and you experience compression on the tension side. So as a result, you develop tensile stress on the other side as well. If you don't provide reinforcement on the compression side of this beam, then when it experiences tension due to these dynamic loads, then the beam shall fail. So to prevent such situations, you provide reinforcement both on the tension side as well as on the compression side in order to resist the effects of stress reversals. And finally, due to resist the effect of creep and shrinkage. Creep and shrinkage. These have long-term effects. So as a result, what happens to the beam? The beam develops cracks due to creep and shrinkage. And as a result, you need some reinforcements to resist such cracks. And doubly reinforced beams are effective in resisting the effects of creep and shrinkage. Now you need to analyze the doubly reinforced beam. Now you have a doubly reinforced beam, you have reinforcements on the compression side as well as on the tension side. Okay. Now you know what is effective depth. Effective depth is the depth small d measured from the extreme compression fiber to the center of the reinforcement layer. And now we are defining another term, d prime. What is d prime? D prime is the distance measured from the extreme compression fiber to the center of the compression reinforcement layer. Okay, and the area of steel on the tension side, we called it AST. Now we call the area of steel on the compression side as ASC. ASC. Okay. Now let this be the neutral axis, and you have the depth of neutral axis as XU. Okay. Now let's draw the strain distribution diagram corresponding to the tension steel, and you have this, you have a strain distribution diagram as shown here. And what is this? Is strain distribution diagram. What is a strain here at limit state? This is the concrete experiences maximum compressive strain. We have learned it as equal to 0.0035, and the strain at the level of tension reinforcement should have exceeded 0.87 Fy by Es plus 0.002. Okay, epsilon St should have exceeded this to become an under reinforced section. Now coming to the stress distribution, we are not at over, we are going to the stress distribution diagram. Okay, on the compression side, the concrete experiences the maximum stress equal to 0.45 SCK. Okay, and what about the steel on the tension side? It experiences a force, a stress of 0.87 Fy. Okay, point experience, because due to under reinforced section, the steel has already yielded on the tension side. But this is not over. You have drawn the compressive stress distribution as well as the tensile stress distribution. This due to concrete and this due to steel. But we are left with the steel on the compression side also. So what to do with that? So there is a compressive force due to that steel also. So let us call it CS. So CS is the compressive force due to steel, compression steel. Now we can have a compressive force due to concrete. Let us, the effect of this stress distribution of concrete, we take that as a compressive force due to concrete as CC. And what is the tensile force at the level of tension steel? Let us call it as capital T. Okay. And now we are going to write what is CS, what is CC, and what is T. What is CC? The compressive force in concrete. This we have already learned. It is equal to 0.36 FCK BXU. What is CS? It is the stress in the compression steel into the cross-sectional area. Stress in the compression steel, let us call it as FSC, stress at the level of steel in compression, FSC, into the area of cross-section of the steel, that is ASC. This will give you the stress into area, you will get the compressive force. Okay, but this is not over, because we have to take the effect of, we have to consider the effect of the lack of concrete due to the presence of compressive steel, compression steel. You know that due to the presence of compression steel, there is no concrete in this area. Okay, but we have assumed in CC that there is concrete entirely over this upper portion of the neutral axis. That is why we can write this equation 0.36 FCK BXU. So this equation 0.36 FCK BXU is a compressive force when the entire region above the neutral axis contains concrete, but we know that this region is devoid of concrete. So that effect of concrete here, the force due to this concrete should be subtracted, and that we will do at the level of steel itself. So minus 0.45 FCK into ASC. So the stress at the level of steel here is approximately 0.45 FCK. The stress at the level of steel here is 0.45 FCK in concrete, and that too into ASC. Okay, so that effect of concrete here due to in place of steel is subtracted here. So that is done. And what about the tensile force here? That also we know already, that is 0.87 F by AST. Okay, so these set of equations, it is very, very important. You have to learn it by heart. CC is equal to 0.36 FCK BXU, CS is equal to FSC ASC minus 0.45 FCK ASC, and tensile force is 0.87 F by AST. And at equilibrium, the compressive force should be equal to tensile force. As a result, compressive force due to concrete plus compressive force due to steel is equal to tensile force. So this is inferred from this. And what we will do, we will substitute it here. In place of CC, you substitute this value 0.36 FCK BXU, plus in place of CS we substitute FSC ASC minus 0.45 FCK ASC is equal to, in place of T we write it as 0.87 Fy AST. From this equation, it is possible to write the depth of neutral axis XU. So XU, you will get it as XU, you will get it as equal to 0.87 Fy AST minus FSC ASC plus 0.45 FCK ASC divided by 0.36 FCK B. So this equation, don't by heart this equation, you can write it, you can derive it from this. You just have to find CC, CS and T separately and equate it. C is equal to T, and from which you will get the depth of neutral axis. So this is how you determine the depth of neutral axis. So in the above equation of XU, you know that there is a term called FSC, which is the stress at the level of steel which is subjected to compression. And you need to know this value. Where do you get this value? FSC. FSC, you can get it from SP16 charts. SP16 chart, page number 13, table F. So this is the table F on page number 13. You can get a copy of this page and get it attested. You see this table for different grades of steel. You can find FSC. This is applicable in case of a balanced section. This is not for an under reinforced section or over reinforced section. This is for a balanced section. Yet you can assume these values for other section also. So you can assume that the given section is a balanced section for the time being and take these values for your analysis purpose. Okay, so how do you take it? These are actually the FSC values, and to get this FSC value, to choose a particular FSC value, you need to know the grade of steel, as well as you need to know the value of this ratio D prime by D, D dash by D or D prime by D. You should know D prime and D. We have already defined these terms, and once you know this ratio, a suitable value may be taken or chosen from the given table. Okay, so FSC you will get like that, and once you get the value of FSC, you can write the moment resisted by this doubly reinforced beam. The ultimate moment of resistance of doubly reinforced beam can be written as equal to, we know that this was the stress distribution diagram. You had compression at the level of steel and you had compression at the level of concrete and you had a tensile force. Okay, now you know the distance between the compressive force at the level of concrete and the tensile force, and you call it the lever arm. And what is that? It is d minus 0.42 xu. D minus 0.42 xu. And this one, you know, what is this? This is the effective depth, small d. And what is this? This is the distance d prime. And now you can find what is the distance between the compressive force at the level of steel and tensile force at the level of steel. What is this? This is d minus d dash. Okay, so you have found both the lever arms. Lever arm between compressive force at the level of concrete and tensile force, that is d minus 0.42 xu, and the other lever arm, that is the compressive force at the level of steel and tensile force, that is d minus d prime. So once you know these values, you can easily write the ultimate moment of resistance. So you have two compressive forces, one is Cc. So what is the lever arm concerning the compressive force at the level of concrete? It is d minus 0.42 xu plus Cs. You have another compressive force, that is Cs. What is the lever arm concerning Cs? That is d minus d dash. Okay, so this is the equation for the ultimate moment that can be resisted by a doubly reinforced beam section.